Good day, grade 12. I hope you are doing well and you're home safe. So here with me, I have question 5 from a past exam paper. We are going to look through the question 5, which is 25 marks. And this comes from the topic of functions. Okay. So first of all, when we look at question 5, we notice that question 5 is on a hyperbola. All right. So hyperbola is one of the functions that you need to know for your exam as well as for your future assessments. All right. So regarding a hyperbola, I've discussed before that a hyperbola has two pieces. It's a two-piece function, all right, which are separated by two asymptotes. So we have asymptotes, a vertical asymptote and a horizontal asymptote. So an asymptote, remember, is a dotted line or an imaginary line that a function will approach but will never touch or cross. And then another thing is that a hyperbola has a general equation which is y equals to a over x plus or minus p plus or minus q. All right. So you need to know and understand the function of a, p, and q. What do they stand for, and how do they help you to sketch a hyperbolic function? All right. So first of all, let's start with a. If your a is greater than 0, meaning if a is positive, then the two-piece functions of a hyperbola will lie in the first and the third quadrants of the asymptotes, all right? Not the first and the third quadrant of the Cartesian plane. Here we are talking about the asymptotes quadrants. So if your a, which will be a number, is positive, all right, then the two-piece function will lie in the first quadrant as well as the third quadrant of the asymptotes. And then if a is negative, meaning if a is less than 0, then the two-piece function will lie in the second as well as the fourth quadrant of the asymptotes. That is very, very important because it will help you to be faster in terms of sketching your hyperbola. And then I've already explained that an asymptote is a dotted line which a graph or a function will approach but will not touch or cross. Okay. Then when you look at your general equation again, we've got variables p and q. We need to know what do they do to a function, a hyperbolic function. All right. So the part that says x plus or minus p, when we equate it to 0 and we solve for x, okay, let's go back to the general equation, this part here, okay. So when you take that part and you equate it to 0, then you solve for x. What is it that you are finding? You are finding a vertical asymptote. I wrote it as VA, shorthand for vertical asymptote, okay. And then when you go back to your general equation again, and then you say y is equals to the value that will be there representing q, what is it that we are finding? We will then be finding our horizontal asymptote. Okay, hence I said to you, a hyperbola will have two asymptotes, a vertical asymptote as well as a horizontal asymptote. Furthermore, when we look at question 5, this is one of the questions where you are given marks, 3 marks as a grade 12, because question 5 will always be a question from grade 11. All right. So that is why in grade 11, we always emphasize that you need to take note of the things that we do in class very seriously, because of in grade 12, they are also examinable. All right. So your question 5, which is on hyperbolas, which is on parabolas, which is on straight lines or linear functions, as well as exponential functions, those are grade 11 content, and they form part and parcel of your exam. All right. Now, let us quickly go and answer the exam question, and see how many marks you can get out of the 25. So at home, where you are, pause the video, do the questions, then check your answers after you have completed answering the questions. All right. Now, when we look at 5.1, we are given f of x equals to 1 over x plus 2 plus 3. When you look at the top there, 1 is positive. Already we know our two-piece function will be in the first and the third quadrant of the asymptotes. Then x plus 2, when I equate it to 0, it will be x equals to minus 2, and that gives me my VA, which is the vertical asymptote. Then when you take your y and equate it to 3, that gives you your HA, which is your horizontal asymptote. Remember, a hyperbolic function has two asymptotes, a vertical asymptote as well as a horizontal asymptote. Okay, now 5.1.1, determine the equations of the asymptotes. Okay, underline equations of the asymptotes of f, meaning the question is asking you to write down the two asymptotes which we have in this case. All right, so you must give me the vertical as well as the horizontal asymptote equations, and I think we have already answered that question. Let us quickly look at the solution. So we said you take that denominator part, x plus 2, equate it to 0, then your x equals to minus 2. That is our vertical asymptote. Very important for you to indicate to the marker what is it that we have written down. Okay, and then the other one we said y equals to 3, and that gives us our horizontal asymptote. Well done. Now 5.1.2, write down the y-intercept of f. Okay, now there's an easy way of remembering what do we mean when we talk about the y-intercept. The y-intercept of a function or a graph is where the graph cuts the y-axis. Okay, so remember, when you have a graph, your graph will either cut your x-axis at a particular point as well as your y-axis. So where your graph cuts the y-axis, we call that point your y-intercept. That's where the graph is intercepting with your axis. Okay, then where your graph is cutting the x-axis, we call that particular point your x-intercept. So remember, along the y-axis, all your x values will be equal to 0, as we have discussed in class. Okay, that is prior knowledge that you needed to know and master so that you can be able to understand this part. Okay, so write down the y-intercept of f. What do we do? Remember, if we are looking for the y-intercept, along the y-axis, all the x values are equals to 0. So y-intercept, we let x be equals to 0. Now, when we look into that one, in terms of writing, we see that f at, remember it was f of x, but because now we are letting x be 0, meaning wherever there is x, we are going to put 0. So f at 0 is equals to 1 over, it was x plus 2, but because of we are letting x be 0, therefore we're going to have 0 plus 2, and then plus 3, then 1 over 2 plus 3, we are getting 3.5, which is the same as 7 over 2. So when you write it in a coordinate form, then your y-intercept will be 0, 7 over 2. All right. Now 5.1.3, calculate the x-intercept of f. Remember now, we are doing the opposite. When we are finding the y-intercept, we let x be equals to 0. When we are finding the x-intercept, we let y be equals to 0. So in this case now, we are going to let y to be equals to 0, and then we find the value of x, where the graph is cutting the x-axis. All right. Now, this is how I've worked it out. X-intercept, let y be equals to 0, meaning where there is y, now I'm going to substitute with a 0. Okay. And then whenever we deal with a hyperbola, the first thing that we need to remember is, especially when you're finding the x-intercept, start by transposing your constant. Okay. Now, when I transpose my constant, it changes sign. It becomes a minus 3. And then all equals to 1 over x plus 2. Then, this is the grade 1 stuff, where you need to make x subject of the formula, and then solve for x. Therefore, my x-intercept then is negative 7 over 3 is to 0. That is where the graph will be cutting the x-axis. All right? Now, 5.1.4. Now, the question says, sketch the graph of f. Remember, whenever you have to sketch a graph, you need 4 things. Number 1, you must have an idea of how the graph will look like. You need to know the shape or the shapes of each and every function. Okay. Number 2, you need to know the y-intercept. Number 3, you need to know the x-intercept. Then lastly, you need to know any other property which relates to that particular function. For an example, an exponential function has 1 asymptote, but a hyperbolic function has 2 asymptotes. A parabola doesn't have an asymptote. Straight line doesn't have an asymptote. Those are properties that you need to know as you will be sitting for your exam. All right. Now, 5.1.4, you are asked to sketch the graph. Not only that, but the question further says, clearly label all intercepts with the axis and any asymptotes, meaning you need to show your x and the y-intercept on your graph as well as any asymptotes. Obviously, there are asymptotes and we have found them there too. Okay, so this is how I've sketched my hyperbola. Remember, when you pause the video, you get a time to do it on your own, then compare with my graph. Okay, so I've indicated where my y-intercept is. I've indicated where my x-intercept is. And I've also shown the marker where my asymptotes are. Okay, there is one which is x equals to minus 2, and the second one which is y equals to 3, and I've represented those as dotted lines in the sketch. Okay, very, very important. Well done. Now, 5.2, you are given a diagram. Remember, when we deal with functions geometry, we may give you a diagram, or you may need to produce a sketch on your own. For example, 5.1, we gave you equations and you needed to produce a sketch to us. But I can also give you a sketch and you need to be able to work even with a sketch. Okay. Now, 5.2, sketched below are the graphs of k at x equals to ax squared plus bx plus c. Now, as a math learner, you need to know, what does that general equation represent? It represents a parabola. A parabola is given in that form, ax squared plus bx plus c. All right? And then h at x equals to minus 2x plus 4. What is that? That is a straight line function or a linear function. Okay, because the highest exponent of the variable is 1, whereas for the parabola, the highest exponent of the variable is 2. That's how we know whether it's a parabola, whether it's a cubic function, whether it's a straight line, a hyperbola, exponential, etc. Okay, now in this case, we've got only 2 functions, and those functions are a parabola, which is this one, and a straight line, which is this one. Okay, now graph K, which is a parabola, has turning point minus 1 is to 80. Very important, because I can be able to find what we call the axis of symmetry if I have the turning point coordinates. Remember, axis of symmetry is a line that I draw, okay, such that my parabola will form mirror image of itself. All right. So my axis of symmetry in this case would be the equation x equals to minus 1, because that's where I get the mirror images of the 2 pieces that I've cut from the parabola. Okay. Now, the other thing is f is the x-intercept. We see it there. X is the x-intercept of h and k, meaning that is a point of intersection. Graphs h and k also intersect at t. Okay. Remember, what do you know about these 2 points? These are points of intersection. Now, it means when we want to find those points or the coordinates of t and f, we need to conduct our simultaneous equations. Remember, simultaneous process is all about finding the point of intersection of 2 graphs. Remember? Okay. Now, calculate the coordinates of S. So, where's S? Well done. S is the point of intersection. But remember, we don't know the equation of the parabola, and we cannot really say the equation of k equals to the equation of h, right? But I know something. If this is a straight line, then I know where the x-axis is cut by that straight line. That is my x-intercept. Meaning I can take the equation there and then find my x-intercept. Okay, let's do that. Now, the first part is we are going to check how to find the coordinates of S. So I said x-intercept, let y be equals to 0, and then I found that my coordinates of S were 2 and 0. Done. Now, another thing that I want to discuss with you, I have some few notes here for 5.2. Just before we continue, let's look at the notes. Now, in 5.2, I think I've already said it. We are having a parabolic function, very important. And with a parabolic function, this is the standard form or the form of an equation of a parabolic function where the highest exponent of the variable is 2. That's how we know that we are dealing with a parabolic function or a quadratic function. And all parabolas have 2 x-intercepts. Very important, okay? And there is one turning point. And it's very important to know what happens with A. A, if it's positive, and then your parabola will smile. If A is negative, then your parabola will be sad. Okay, so when your parabola is smiling, we say it's concave upward. And when your parabola is sad, then we say it is concave downward. Okay, and moreover, you need to know what is the function of B. Okay, so if your B from the general equation here, from here, if your B is positive, then you need to know that your parabola will mostly be closer or more to this side. Okay, very important. And then if your B is negative, then your parabola will be more to the left-hand side. Okay, very important. Remember, to the right-hand side, more positive. To the left-hand side, more negative. So your B tells you to which side will your parabola be most at. Okay, and then from the general equation again, we have this value here, which is C. C represents a constant, and that constant is what we call a y-intercept or a y-cut of your parabola. Okay, very important. So when you've got a standard form of a parabola, your C represents the y-intercept of the parabola, and C is a constant, meaning C won't have a letter with it, meaning it won't have a variable with it. Okay, very important. Then when C is positive, what does it mean? Since C is a y-cut, it means then your graph will cut the y-axis above the x-axis, meaning it will be cutting your y-axis, the part of the y-axis which is above the x-axis. Okay, and then if your C is negative, there we go. If your C is negative, then your graph will be cutting the y-axis below the x-axis. All right, very, very important. And then since we also have a straight line, this is the equation of a straight line. Okay, that's how we see straight lines with the highest exponent of the variable being 1. And then we can write the equation of a straight line in two forms. But you must always simplify it to this point, okay, or to this part. Now, the two forms are, this is the first one, where you can first find the gradient, which is your m, your average gradient, and then substitute a point, then you get c. Or you can use this second form of a straight line, where y1 as well as x1 will be any point that lies on the straight line, okay? And remember, m is your slope, or what we call your gradient, okay? Very, very important. And then lastly, what do we normally do? We either call your m, which is y2 minus y1 over x2 minus x1, a gradient, or sometimes also call it average gradient, but it means one and the same thing. So the formula of calculating a gradient is m equals to y2 minus y1 over x2 minus x1, or it is change in y over change in x. Okay, so with straight lines, there is one x-intercept and we have one y-intercept. Okay, and remember, we have a c in that general formula of straight lines. There is the c. Then what does the c stands for? The c stands for the same thing as parabolas, which is the y-cut or the y-intercept. Okay, and then when c is positive, then it means the graph cuts the y-axis above the x-axis, okay, meaning on the positive side of the y-axis. And then when c is negative, then the graph will cut the y-axis on the negative side of the y-axis, okay. And then another thing that you need to make sure that you understand is that with straight lines, we have only one x and one y intercept. Okay, very, very important. Now, lastly, when the gradient of a straight line is positive, the straight line will look like this. Okay, and then when the gradient of a straight line is negative, then the straight line will look like that. Those are shapes of straight lines depending on whether the gradient is positive or it's negative. So the gradient plays a major role in determining the shape of your straight line or your linear function. Then we have other functions like exponential function as well as cubic function, but we are not discussing that in this presentation. And also there's what we call a logarithmic function, which is known as the inverse, the opposite of exponential function along the line y equals to x. Okay, those are mirror images of each other. Exponential function is a mirror image of a logarithmic function. And then we deal with cubic function when we deal with calculus, okay, which we'll discuss in another presentation. Now, having said that, it's very important to note this. Please go through this. I think I've already explained about parabolas and straight lines. So this is with regards to the question at the hand, the question that we are dealing with. Okay, so I've just written down some few notes looking at what we have. Okay, now let's go to 5.22. Determine the equation of k. What is k? K is our parabola. And this should be in the form y equals to a times x plus p all squared plus q. Okay, I'll quickly like to go to the last slide so that we can discuss something. Okay, look at this. Did you know that with parabolas, we can write equations of parabolas in these forms, three forms. There's what we call a standard form, there's what we call an intercept form, there's what we call a turning point form. So what are these forms? These forms of equations of a parabola depend on what is given. Okay, this one works best, number 3 works best when you're given the turning point of a parabola, of which the coordinates will be represented by P and Q. Those will be the turning points of a parabola. Or when you're given two intercepts and another point that lies on the parabola, and then we'll be using number 2. We call that the intercept form. Then usually number 2 and 3 will always simplify to the standard form. Standard form also works best when you're given some information like A and maybe another intercept as well as the y-cut, etc. So these are 3 different forms that we can write the equation of a parabola, but they will always simplify to the standard form. And with the parabolic or the turning point form, we normally use our completing the square to find that form. Okay, now having said that, the question in 5.2.2 is asking you to find the equation of k in the turning point form. Do you have the turning point? Yes, that is our minus 118, and then this is how I've done it. Okay, now turning point form requires you to have a turning point. I have a turning point which is minus 1 is to 18. Then k at x equals to a. X, take note, as a coordinate it was minus 1, but when you write it in here, you must write it in reverse, such that you imagine yourself solving for x. Remember, if I were to solve for x there, x plus 1 equals to 0 will then become x equals to minus 1, right? So please make sure you don't write x minus 1, because when you solve for x, it won't give you minus 1, okay? It will give you a positive 1. And then 18, you write it as it is, okay? This is plus 18, and I have a plus 18. But remember, the equation, we need to know what is the value of a by substituting a point that lies on the function k at x. So I substituted s, which is 2 is to 0, because s was actually the one of the x-intercepts of the function k. Okay, now having substituting my s, then what I found was that my k at x equation then simplified to this. My a was a minus 2, then I substituted my a back where there was a, and then the equation in full became minus 2 all multiplied by x plus 1 squared plus 18. Okay, very, very important. Now, having done that, let us go to 5.3. In 5.2.3, they are telling you if k at x equals to minus 2x squared minus 4x plus 16, this is now when we have simplified from turning point form to the standard form. Do you see that this is the standard form of a parabola? Yes, okay. Now, if k at x is that, determine the coordinates of t. Remember, what did I say about t? I said t is the point of intersection of the parabola and the straight line, meaning we can equate the 2 equations. Now, when we equate the 2 equations, we find that we have minus 2x plus 4, which was the equation of h, and then equal to minus 2x squared minus 4x plus 16, which is the equation of k. Then we wrote this in standard form, which became x squared plus x minus 6 equals to 0, and then we found that our 2 values of x were x equals to 2 or x equals to minus 3. But remember, when you look at the diagram, where is t? T is in the second quadrant. And what do we know about the value of x here? It's a negative. So that means t, the value of x for t can only be our minus 3, right? Because the x value of t is a negative. And then how do we find the y value? We substitute that x value to one of the equations. Okay, you can either substitute on k at x or h at x. Hence I said h at minus 3, which is my x value of the intercept, and then I found that the y value of the intercept was 10. What does it mean? It means minus 3 and 10 are the coordinates of t. Okay, those are the coordinates of t. T is minus 3 is to 10, which is correct because we can expect 10 to be somewhere here, somewhere there, and then we expect a minus 3 to be somewhere there. Okay, so that makes sense and we are happy. Now the next thing is determine, that is 5.2.4, determine the values of x for which, look at this, k at x less than h at x. What is the meaning of this? Very important for you to understand. Where will the graph of h be on top? You see, they wrote it as k at x less than h at x, or you can say h at x greater than k at x. But what is the meaning of this? The meaning of all of this is find the values of x where the graph of h will be on top of the graph of k. Okay, let's look at that one. So when I look at this sketch, I notice that the graph of h there is on top of k and also somewhere here. That's what the question is asking me. So I need to write down the values of x where the graph of h is on top of the graph of k. Okay, so let's do that. Already we have seen that the graph of h will be on top of the graph of k, where from minus infinity up to minus 3 and from 2 up to positive infinity. Let's look at that. Yes, remember the graph starts somewhere there, which is negative infinity, but will stop somewhere there at minus 3. You remember, we are talking about the values of x. So it will stop there being on top of the graph of k. Then here we don't have anything here because the graph that is at the top is k being on top of h, and that is not what the question is asking us. But also we notice that if we are to continue with our parabola here and the straight line there, the straight line will also be on top of the parabola. So as a result, it means the other value of x or values of x where h will be on top of k is here, and that is all the way down there and down there. So h will be on top of k also there, which is what? Remember, s was 2 and 0, meaning from 2 up to positive infinity. You see that? Good. Now, moving on, 5.2.5, it is further given that k is the graph of, look at that, is the graph of g derivative of x. So k, the parabola itself is the derivative, meaning it is k at x and it's also g prime at x, meaning it acts as a parabola in our case where it's k at x. But when we go to polynomial functions, when we go to calculus, now it's a derivative of a cubic function. All right, very important. Now make sure you have covered your derivatives and your cubic functions so that you can understand what I'm talking about. Now they are saying, for which values of x will the graph of g, what is g? Remember, g will be the cubic function. Okay, remember they told you that g derivative of x is the parabola, meaning g of x will be the cubic function, the higher function. Okay, now they are saying for which values of x will the graph of g, the cubic function, be concave upward. Okay, now remember, since my parabola looks like that, it is a set parabola, then it means my cubic function will look something like that. You agree with me? Where the turning point of the parabola will be the point of inflection of the cubic function. And we notice that our cubic function will then be concave upward. Where? Will be concave upward here, up to the, okay, just before it changes concavity. So where is this? This is from negative infinity up to the value of x of the point of inflection, which is minus 1. Okay, so from negative infinity up to minus 1, that's where our function g will be concave upwards. Okay, now let's look at that. I've written it down. I've said 5.2.5, if k is the derivative of g, then g at x is cubic. I've already said that. And cubic functions are given by this form of an equation, where if a is negative for a cubic function, then the cubic function looks like that. Okay, like in our case, since our parabola is a set parabola, that makes our cubic function to also have the value of a as negative. Look at where I have shown you the point of inflection. You see the point of inflection? That is up to there where the graph will be concave upward. So that means x will be an element of from negative infinity up to where x is equals to minus 1, because from minus 1 up to positive infinity it will be concave downwards. This is where I'm talking about. Okay, or if you don't like writing it in this fashion, then you can write it in this fashion. Okay, please, normally I call the these are what we call your set builder notation as well as your interval notation. Okay, so you can choose any one of the two. You don't need to write both of them because they mean one and the same thing. Okay, and then now for B, 5.2.5b, sketch the graph of G, showing clearly the x values of the turning points and the point of inflection. Remember, when we go to cubic function, what is the relationship between a cubic function and a parabola? This is the relationship. The x-intercepts of a parabola are the turning points of a cubic function. And the turning point of a parabola is the point of inflection of the cubic function. Okay, very, very important. So it means the first thing, I know what is s, which is 2 and 0, but I don't know what is the other x-intercept there. So mine is to first find the x-intercept there. Okay, so let's start there. So x-intercept, let y be equal to 0 on the parabola. Then I found that my two x-intercepts are x equals to 2 and x equals to minus 4. But remember, I already have the x equals to 2 from s. What I'm looking for is actually x equals to minus 4, right? Then what did I say about the x-intercept of a parabola? Those will be the turning points for a cubic function. There we go. You see that? Those are now your turning points for the cubic function. Okay, those will be your local maxima, which is the top one, and this will be the local minima, okay, or relative maximum as well as relative minimum. Those are your turning points. Two turning points for a cubic function, very, very important. Okay, now look at where minus 1 and 18 is. That is our point of inflection, where the cubic function changes concavity from being concave upward to being concave downward. Okay, we call this the point of inflection. Now, lastly, I think I've already discussed this. You need to make sure you understand that a parabola has three forms that you can write it in, provided on what is given. There's a standard form, there's an intercept form, turning point form. So with the standard form, we can give you a point that lies on the parabola as well as maybe the y-intercept. Okay, and then with the intercept form, we will be giving you two x-intercepts and another point that lies on the function, so that you can be able to find a. Then with the turning point form, we'll give you the turning point, which is represented by the coordinates of PQ. Okay, PQ represents the turning point. So when you're given the turning point form, then this is the form of the equation of a parabola that you must use. And please make sure you watch the other revision sessions which I have. Good luck.